Okay, what we're going to do today, we're going to talk about Tuesdays and Thursdays lab today. Thursday, we don't have that much time. And so we'll start off with Thursday's lab. I'm going to modify the procedure since we're going to have the lab followed by the exam. You don't actually have to prep your lab notebooks for this because it's going to be pretty straightforward. We aren't going to use the indicators. We're just going to use pH meters to measure it, pHs. But before we use the pH meters, we're going to calculate the pHs for these. And so if you look at hydrolysis of ions and buffers, all the solutions are 0.100 molar. And so we're going to determine the pH. This would be Thursday's experiment. And then you'll do some calculations today, and then we'll talk about today's experiment after this. So what do you need to determine the pH for? We're going to have sodium acetate. Actually, do we do water first? DI water? Or does that come later? Water's first? DI water? So we do DI water. What should the pH be? 7. pH should be 7, but our DI water is contaminated. You know what it's contaminated with? It's contaminated with CO2, carbon dioxide. This can't be avoided. This is why our barium hydroxide always has a white precipitate in there, because there's CO2 in air. You know. In fact, if you were to take a straw and blow bubbles in the water and measure the pH would go down. It would become increasingly acidic. And so since it's contaminated with CO2, the pH is more around 5, 5.5, 4.5, something like that. So the pH is less than 7. Well, what's one way to get rid of CO2 contamination? Yeah, you drive it off by boiling it. And so we have boiled water. We should drive off any dissolved gases that are present. The dissolved gases would be like CO2, nitrogen, oxygen. But nitrogen and oxygen don't change the pH, so primarily we try to drive off the CO2. And so if you use fresh boiled water at room temperature, the pH should be 7. Problem is it's going to resaturate with CO2, so you know, if you leave the stopper off, pH will go down. Also, you know, over time the pH is going to go down because people opening and closing the container is going to reintroduce CO2. All right, so we try to minimize that by keeping the jar closed when not in use. Okay, the next solution is sodium chloride. What's the pH of sodium chloride? Yeah, this should be pH 7. It should be pH 7 because sodium ions are neutral and chloride ions are neutral. So neither of those hydrolyze water to any significant extent. The next solution is sodium acetate. All right, sodium ions are neutral, acetate ions are basic. So we expect the pH should be greater than 7. And so we're going to calculate the pH for this and then measure it. And so acetate can hydrolyze water. You produce acetic acid and hydroxide. All right, Kb for this is equal to Kw over Ka for what acid? Acetic acid. Kw is 1.0 times 10 to the minus 14. Acetic acid is 1.8 times 10 to the minus 5. This gives us a Kb of 5.5, so 5 times 10 to the minus 10. And so it's pretty small. It's not all that basic. Okay, so let's do the calculation. We have 0.100 molar acetate, 0 and 0 to the products. Change is minus X molar, plus X molar, plus X molar. And so at equilibrium, we'll have 0.100 minus X, and X, and X. The same setup. I'll plug this into the Kw expression, which is the acetic acid concentration times the hydroxide ion concentration divided by the acetate concentration. So our Kb expression, which is equal to x squared over 0.100 minus x. Simplifying assumption should work well here. K is very small, and we have a fairly large concentration at 0.100. So this is going to simplify to x squared over 0.100, and x will equal, can somebody calculate it out? .449. 7.49. Did you round that, or is that? 7.449. Oh, 44. All right, 7.44 times 10 to the minus 6. So most of the acetate remains. So times 10 to the minus 6, I need 5 zeros. So 1, 2, 3, 4, 5, 7, 4, 4. Gives me a 6, 5, 2, 9, 9, 9, 9, 0. Just a small amount. In fact, if you look at the percent change, it's 0.007% change. And so it's a very small percent change. Much less than 5%, meaning that our simplifying assumption was no problem. And then the acetic acid concentration will be 7.44 times 10 to the minus 6 molar. And the hydroxide concentration, 7.44 times 10 to the minus 6 molar. So we should double check these concentrations to make sure we didn't make any mistakes. And so just make sure the K checks out. Yeah, that's good. Okay. All right, the next question we ask is, are there any other hydroxide producers? This is a base solution, so we look for hydroxide producers. Water. Should we worry about water? Oh, why or why not? Usually we look at the hydroxide here and then ask ourselves, will water contribute a significant amount of hydroxide to this? And so what's the most hydroxide we're going to get from water in a base solution? 10 to the minus 7. So if that's the most and we have 10 to the minus 6, then maybe we should worry about water. But let me give you a better feel for it. Water at the most is 10 to the minus 7, but usually it's going to be much less than that, 10 to the minus 8, 10 to the minus 9. If we're getting 10 to the minus 8, 10 to the minus 9, then maybe it isn't so significant. And so when should you start worrying about water contributing hydroxide? When you start worrying about water contributing hydroxide is when this is like 10 to the minus 7 or 10 to the minus 8, then I'd worry. 10 to the minus 6, I probably wouldn't worry. 10 to the minus 5, would you worry? No, not at all, because it's a big amount. And we're going to get very little from water. But You know, since 10 to the minus 6 is kind of borderline where we might start to worry, let's go ahead and calculate the additional contribution of hydroxide from water. And so what we're going to do is we're going to go ahead and do step 2 here and see if water contributes a significant amount of hydroxide to step 1. And so we're going to carry this one down to step 2. It's going to be 7.44 times 10 to the minus 10 molar. And hydronium is 0 molar. So this is going to be plus X molar, plus X molar. And so X molar and X molar. Oops, no, 7.44 times 10 to the minus 10. 10 to the minus 6, sorry. 10 to the minus 6 plus X. Well, you know, this is the common ion effect. If we didn't have this common ion here, then we would get 10 to the minus 7. Since we have this common ion here, we're going to get a lot less than 10 to the minus 7. A lot less. And so, likely I don't have to worry about it. But let's just do the calculation so I can be sure. Okay, so Kw is going to equal the hydronium ion concentration, X, times the hydroxide ion concentration. 7.44 times 10 to the minus 6 plus X. We'll just go ahead and use the simplifying assumption. So this is going to be X times 7.44 times 10 to the minus 6. And this is going to equal 1.0 times 10 to the minus 14. And so X is equal to what? To the negative 9. So we said that the maximum additional hydroxide we're going to get from water is 10 to the minus 7. That's correct. The reality is we get a lot less, you know, 10 to the minus 9 additional hydroxide. And so does that really make an impact here? So let's figure it out. 1.34 times 10 to the minus 9 molar here for the hydronium. And then the hydroxide is going to be, I need 5 zeros, and then a 744. Okay, plus, I need 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8, and a 1, 3, 4. And so I end up with 0.5 zeros, 7, 4, 4, 1, 3, 4. So I started off with 7440, and I end up with 7441. Is that a significant change? No, did we? Yeah, we barely got anything from step 2, so we really didn't have to do step 2. Excuse me. And so if your hydroxide or hydronium is 10 to the minus 6, then water is not really going to contribute to that. It's only when you get to like 10 to the minus 7, 10 to the minus 8, and lower that it will contribute. The other thing that's good is, did step 2 perturb step 1? No, because the change in the hydroxide was so small, it really doesn't upset step 1. Otherwise, we'd have a simultaneous equilibrium situation on our hands. So we better double check these numbers to make sure K checks out. Did it work out? Double check. Yeah? No? It does or it doesn't?
It does, but it's 9.97 times 10 to the negative 15.
Oh, okay. So K comes out to 9.97 times 10 to the negative 15, which equals 0.997 times 10 to the negative 14. And so that rounds to 1 times 10 to the negative 14. So we're okay. This checks out. So it's good. All right, if I'm going to do a solution inventory, then I want all this. Although I'm missing one species for the inventory. What species am I missing? I'm missing sodium ions. I skipped over that. The sodium ions are going to be present at 0.100 molar. So I went straight to acetate. The acetate is close to 0.100 molar. Then we have some acetic acid here. And then the hydroxide ends up here, this concentration. And then the hydronium here. That would be the inventory. So if we stopped at step 1 and calculated the pOH, and then figured out what the pH is, then it should come out the same as carrying this all the way to step 2 and figuring out the pOH and then calculating the pH. But since we went all the way to step 2, we can just calculate the pH directly. Here we have the hydronium ion concentration. Can somebody calculate the pH? 8.87. So pH 8.87. If we went the route of just stopping here and calculating the pOH and getting the pH, what would you get? Is it the same, 8.87? Well, 5.53 would be the pOH? 5.13? So if we stopped here, we got a pOH of 5.13, which gives us a pH of 8.87. So it's the same either way. Okay. Good. All right. Question I have is, okay, we took care of the hydroxide ion contributors, which would be acetate in water. Sodium ions are neutral, so those don't change anything. But what about this? Acetic acid. Acetic acid is a hydronium ion contributor. And so should we factor in the hydronium ion from the acetic acid and then cancel that with the hydroxide ion? No. Well, why not? Well, you have to add one other thing. You know, that's correct, but sometimes they aren't related. They're only related by Kw. In this case, they're related by something else. I don't have to do acetic acid because kind of. It's not that really. No, not because it's a weak acid. I don't have to do acetic acid because I know the hydronium and hydroxide are related, but in this case, they are related. In other cases, we could generate hydronium from, you know, completely unrelated acid. This acid's related though. The reason why we don't do acetic acid is because it would be redundant. Because if we did Ka for acetic acid, Ka for acetic acid would be acetic acid plus water yields hydronium and acetate. And so the Ka for acetic acid just is the equilibrium between acetate and acetic acid in terms of hydronium. Kb for acetate is the equilibrium between acetate and acetic acid in terms of hydroxide. And so in this case, that's how they're related. They're related because they both describe the exact same equilibrium. Whereas we could have an acid that's totally different and would be describing some other equilibrium, which we'll see shortly. All right, so let's see. Sodium acetate. After sodium acetate comes ammonium chloride. The situation with ammonium chloride is ammonium ions are acidic, chloride ions are basic. Concentration is 0.100 molar, and Ka for ammonium turns out to be the same, 5.55 times 10 to the minus 10. So the numbers come out the same. It's just, the pH would be 5.13 rather than the pOH. It's the same calculation. So we're going to skip that and go to what comes after ammonium chloride. What is it? Zinc chloride. All right, chloride's easy. Chloride's neutral. But what about zinc? Zinc, acidic, basic, or neutral? Zinc ions. Acidic? Acidic is correct. Metal cations are acidic, except for group 1. Yeah, calcium, strontium, barium. Group 1 and calcium, strontium, barium. Good. All right, the problem is we need a Ka for zinc. They don't give us the Ka for Zn2+. So we gotta look it up. Well, I lost the one I was going to show you. But the one I was going to show you had a Zn2 plus of Ka of 33.3. That was on Yahoo Answers. It was the best answer. Is Ka for Zn2 plus of 33.3. What do you think? Does that sound like a reasonable answer? No. That would be a ridiculous answer. 33.3 for Zn2 plus would rank it as a strong acid. If you look at what's borderline strong, like phosphoric acid, that's still 10 to the minus 2, or oxalic acid, those are borderline strong acids. And so K is 33.3, can't be, otherwise you would have learned that Zn2 plus is a strong acid. You would have memorized it as well because it's fairly common. In that same Yahoo Answers page, they gave a Ka for some other weak acid as 10 to the positive 19. 10 to the positive 19. You know what? When I started reading these answers were from the same person. And so when I started reading these answers, this guy's trying to play some kind of joke on this poor student. This poor student has no clue. This poor student's going to use all those answers thinking that they're correct. And this person's just laughing at that. And so there's a lot of unreliable information. Yahoo Answers is full of them, unfortunately. What's that? In what form? It won't form? Oh, zinc oxide? Yeah. Yeah, but we don't hydrolyze it completely. It's not going to hydrolyze water completely. That is, when we look at zinc, the first thing is, why are metal cations acidic? When we look at the periodic table, what do group 1 and calcium, strontium, barium have in common? Well, basically what they have in common is this. The biggest atoms are on the left or on the right side of the periodic table? On the left side of the periodic table. The biggest atoms here. And so the biggest ions, cations, will be over here. These are going to be the biggest cations. And so the cations are going to get smaller and smaller. And so what they have in common are these are going to be the biggest cations. And so if we have a +1 charge on something like rubidium versus a +1 charge on something like silver, there's a tremendous difference in the size. And so these ones aren't really reactive enough to form a complex. So if we're looking at sodium ions and a ligand comes along like water, then typically what happens is water, the ligand, will form a coordinate covalent bond, right? It'll donate a pair of electrons here. But the interaction between sodium and water is weak. And so instead of forming a coordinate covalent bond, what we form is an ion dipole attraction, like this. And this ion dipole attraction is what holds the water molecules to the sodium ion. Whereas if we have Zn2 plus here, and a water molecule comes along, then this is a much stronger attraction here. A 2+ charge on a small atom like zinc is going to be quite reactive, versus a 2+ charge on a big atom like calcium is going to be a lot less reactive. And so what can happen is we can form a coordinate covalent bond here, Zn, then OH, this. Zinc is still 2+, and since zinc is 2+, what can happen here is that we can get electron density pulled out of water and pulled in towards zinc. And so we're going to get something called the inductive effect happening here. And so zinc 2+ is actually going to pull electron density away from oxygen, making oxygen more electron poor, which in turn is going to pull more electron density from hydrogen. And so what this means is that in a water molecule like this, where the electron density is being pulled towards the oxygen, the delta plus on hydrogen is like this. But in a water molecule like this, the delta plus is going to be much larger. And since that's much larger, it's going to make it more attractive for bases. And so a base can come along here. Let's see, any other? Some pens. Like water. And pluck that proton off and leave these electrons behind. And so it's going to form zinc 2+, but now with the hydroxo ligand rather than a aqua ligand. And then the water is going to be converted into a hydronium ion. Okay, hydroxo is -1, zinc is +2, so this is going to have a net charge of plus. Sure. That's just with one aqua ligand. That's all I'm showing here. This would be the Ka. And so what we got to do is we got to figure out how many aqua ligands can bind to Zn2+. It could be 2, 4, or 6. And so how would you know? Well, you wouldn't necessarily know. You just look it up. And so we look it up in a book, and we see that it turns out we'll have 6 aqua ligands. And so the net reaction, Ka reaction, is hexaaqua zinc 2 plus H2O liquid yields the hydroxo pentaaqua. Actually, how would you name this? Would it be pentaaqua hydroxo, or would it be hydroxo pentaaqua? Yeah, we do pentaaqua hydroxo zinc 2 plus hydronium. Then we'd search for a reliable K value. And so looking for K value, I found one. And the K value, they write it as a pKa, and they give us a pKa of 9.4. You know, this is still not totally reliable data, because there's also pKa values that are listed at 8.3. And so there's a range of pKa values that are listed. But we'll take this one at 9.4 for the purposes of our calculation. And so that's a power function. And so that tells us the Ka is between 10 to the minus 9 and 10 to the minus 10. If I want to calculate the Ka from a power function, the Ka is just 10 to that power function, the negative of that power function. And so this is 10 to the minus 9.4, which gives us a Ka value of what? 3.98 times 10 to the negative 9? Negative 10? 3.98 times 10 to the negative 10. That's right. And so 10 to the negative 10 means that zinc 2+ is a weak, very weak acid. This, what would you say, very weak or just a weak acid? Very weak. I mean, 10 to the minus 10 is very weak. And so it turns out that ions like this are polyprotic in nature. And so this would be Ka1, but Ka2 would form the zinc hydroxide, which would be the precipitate. But that step would be even worse off. It might be close, but it's probably, even if it's close in terms of the pKa, it's still going to not be a very significant contributor. So we just look at the first step for this one here. All right, any questions on this? I'll let you do the calculation. So why don't you work on the calculations for the first part of the lab here. This lab really only takes about an hour to do. And so I'll talk about it for about 15 minutes, and then we'll finish up the lab. And so you'll have, let's say, at least an hour for calculations. I'm sorry? Oh, today we're going to do Le Chatelier's principle. But right now what we're going to do is we're going to do pH calculations for Thursday's lab. And I'll give you some time to work on those, and then I'm going to come back and I'll talk about today's lab, Le Chatelier's. Okay. All right, any questions? No?